So that was the discussion of the definitions and taxonomies. They actually didn't fully finish on the 30th of September, and they're finally wrapping it up now. Now let's look at the reference architecture, which is also unfinished. A lot of new work still needs to be done here, although good progress has been made in identifying the key features of a reference architecture. So remember, we have to do the, it has a charter. It starts off with the generic charter about community of interest, covering industry, academia, and government, being agnostic as to everything. So we play no favorites. And then we want to produce the reference architecture that somehow allows this competition between IBM and Apache and Microsoft and the different research groups at universities and the different compute providers. And so we need to study what people have done now, what they call big data, and notice that they actually are solving different problems, and not all architectures are good for all problems. And then we need to, that's where the taxonomy comes in, because it allows us to classify things and divide everything up by actors and roles, and then build an architecture, which we call the reference architecture, which is generic, which can have the security and privacy architecture, which we'll discuss later on, laid on top of it in a consistent fashion. So as appropriate, this subgroup started off by looking at lots of different architectures. We had some which are called vendor neutral and technology agnostic generic architectures from Bob Marcus, Dorit Levin, Gary Mazzaferro, and Yuri Demenchko. You know, there's three commercial and one academic. Then we looked at the vendors architectures, which cover a variety of different types of vendors: IBM, Oracle, Booz Allen, EMC, SAP, Ninesight, and LexisNexis. Out of all that came a descriptive discussion of architecture, which I won't go through, and then a final sort of summary where it puts everything together. All right, so let's look at the vendor neutral and technology agnostic proposals. These are all documented in individual documents. All those documents are publicly available. If you go to the website, whose URL is in the resources, and actually on one of the slides towards the end of this unit, you will find that there's a whole set of documents starting with the letter M. Probably up to now, I don't know, 270 such documents. And here we have rather low numbers, so this obviously comes from the beginning of the document collection. And these are three of these rather generic architectures. If you look in more detail, this has, as often you see, this is for the IT stack 47 and M0047. You have security as a cross-cutting theme, visualization, analytics, processing, storage. So this is sort of hardware, storage, processing, analytics, visualization, software, and then the actual devices. And of course, the people are sitting here looking at the visualization. So that's one generic architecture. Here's another one which focuses on the data flow and processing, which is especially for sensor data very important, or for so-called streaming data, where the data gets updated continuously. And this focuses more on the collection and the various things you do to it, including data mining. And the final storage. Security, again, is cross-cutting. And here we have the different users of the data here, and the data starts off at the top. And it has these three V's across here: variety, velocity, and volume. Here's a more classic uh, flow diagram, which shows you how these various capabilities are interconnected. We have usual things. We have user interfaces, analytics. Here we have in-memory operations. A critical feature of modern big data is in-memory databases, and a lot of those are accelerated by using a solid-state disk compared to traditional hard disks. Here is a traditional hard disk, and here's one separately for the analytics to use. I pointed out stream processing, and if you're doing database, then we always have extract, transform, load, which is how you get operational data into the data warehouse. We have security here, which is just led us a box here rather than the more sort of ones that try to show security as cross-cutting. There is no, I think, no implications, any difference in the role of security, just the way you just represent it. And here we have management functions and the design and the developing and the deploying of these tools to solve the problem. And finally, at the bottom, we have the infrastructure. So all of these are different proposals, architectures, represent in different ways the key aspects of the whole big data analysis. And so here we're starting to see the formulation of the what you might call the well, is in fact the reference architecture that NIST developed, and this is it represented in a rather very high level form, where we have now identified this concept of a transformation, which is all the functions you do. I mean, transformation is very important because data, as we have said before, data is always transformed. It starts off as raw data, then becomes data, then becomes information, then becomes knowledge, and then becomes wisdom, and then becomes decisions. Each of those steps is a transformation, and that each of those steps can have many transformations needed. So transformations is critical, and so these sources needn't be the raw data, they can actually be what came out of a previous transformation. Here we have the infrastructure where the transformation is executed on. So the transformation spits out data which probably goes either to the user or to another transformation. And now we have the security, the management's cross-cutting, as is, and then we always, remember, we always use cloud computing, that's the motto of the course, and then we do the networking. All right, so now we're going to start, we're going to take that actual picture and annotate it and add capabilities to get the final answer. So here we have the data provider over here, which involves, and then the application provider will probe the data provider to find out about the data, access it, possibly execute code here in data code. That's a common database strategy. And if you had a sensor, you often will run processing on the sensor to reduce data volume. Here's where whoever's consuming the data, that could be another application or the user discovering, describing, visualizing, rendering, reporting, and executing code on the data. So that's what the consumer is telling the system to do. All right, here we have the actual analytics, the machine learning, the code execution, storage, retrieval, the computing infrastructure, the networking infrastructure, etc. And then the final set of components are the system orchestration, which means you have somebody or something, let's call it a workflow system that integrates all this stuff together. And then finally, we get these that dynamic diagram becomes this more static picture we see here. We again have the consumer, the orchestrator, the provider, the framework provider, and the application provider. Here's where if you like, the software is, the analytics and the algorithm. Here's where it all gets executed on horizontally scalable Hadoop clusters or whatever you want, or databases. You might use you expect to use virtual clusters were made out of virtual machines and so on.